Alright, so in this video we're going to take a slight detour and we're going to look at where our moon comes from. This is going to start off by looking at the ages of the Earth and the moon and how we know them. Then we'll consider evidence for the three different hypotheses on how the moon could have formed. So this is the Earth and its moon. The Earth is pretty unique in that it has a very large moon for its size. And this really influences the oceans whenever we think about tides. The moon's orbit around the Earth controls the tides because it's pulling water toward it. So we can ask this question about where did our moon actually come from? How did it become part of our journey through space? So one way we can answer this is by going back to radioisotopes. We can ask questions like, how old is the Earth? How old is the moon? How old is the solar system? So this is basically relying on the very consistent timescale that radioisotopes decay. So for instance, for tritium decaying into helium-3, the half-life is about 12.5 years. So if you wait 12 years, you'll lose half of your tritium and you'll gain an equal amount of helium-3 that results. After 2 half-lives, you have 25% remaining, etc. But what we need is something that's going to stick around a bit longer than 12 years because the moon and the Earth is a lot older, and I hope you know that. So what we can do is find a much slower clock, and we find that in the uranium-238 decay timescale. So uranium-238 is a common form of uranium on Earth today, and it decays regularly to lead-206, whose abbreviation is Pb here. So the timescale here is not on a few decades, it's on billions of years. So the half-life for uranium-238 is 4.47 billion years. So after that amount of time, we've lost half of our starting uranium in the solar system, and we've gained the equal amount in terms of lead. So the actual decay series for uranium is a bit complex, and this has a lot of applications in earth science because you can try to measure all these intermediates. Uranium first decays into thorium, which decays back into a lighter version of uranium, which decays into another version of thorium, and so on. But this all ends up in lead, and the only process that controls this rate is the first decay of uranium-238. And essentially this reaction boils down to 238 uranium turning into 206 lead, and this mass difference here between 238 and 206 is basically balanced by 4 helium nuclei, or alpha particles, that are generated during this decay. So what we need for this, right? Helium is a gas, it'll fly off into space. What we need is a really good container. So one really good container are the meteorites we talked about previously. So these are basically solid metal blocks floating through the sky. These basically hold on to the uranium, the lead that's generated, and the helium that's produced. So this is a good way to sort of have a closed system so you can figure out how much uranium that you started with by adding up uranium and lead, and how much decay has happened since then by tracking how much lead is there. And what's cool is that this, a lot of meteorites have been dated through the uranium and lead decay system, but there's a lot of other long-lived radioisotopes that have been used to corroborate the ages of different meteorites. So some of these are listed here. There's different versions of uranium that decay into different versions of lead. There's rubidium, which decays into strontium. You can see them here. They have very different half-lives, but in terms of the age of these meteorites, they all give pretty consistent answers at around 4.55 billion years or so. So this is where the age of the Earth and the age of our solar system comes from. These meteorites were formed pretty early on during the planetesimal phase of our universe, and so this is where Earth's material sort of came from. So this is sort of where things start at 4.56 billion years ago. Now, this is a great way to study the early objects of our solar system, but what about things on the Earth or on the moon? We need another container. Fortunately, there are other good minerals that serve this function. The best one is probably zircon. So zircon is this zirconium silicate mineral. It's a bit odd, but this is something that is extremely chemically strong. If you're working with these crystals in the lab and you're trying to dissolve them, it's going to take a lot of work to actually degrade them, and there's very few conditions in the environment that will actually degrade zircons. They're extremely long-lived. The other nice thing about zircons is that they incorporate uranium to a pretty nice degree. So this So the U4 plus uranium atom can substitute into the silicon 4 plus space in this crystal structure, and so based on the environment where these zircons can form, they incorporate good enough uranium. They actually don't take up a lot of lead, so they start off on all uranium, no lead, and then they decay as they sort of sit in this closed system. So the oldest zircons that we can find on Earth are in Australia in a place called the Jack Hills. These zircons are dated to be around 4.4 billion years old. So this is around 100 million years after the formation of the solar system. That's when we have the first zircons on Earth. These might date back to the formation of the first crust. But what's cool about this is these are older than the rocks that they're found in. These are crystals that are found within rocks that are younger than the zircons. Those zircons are more long-lived than the oldest rocks on Earth. Now, during the Apollo missions, they were really motivated by geology, and so a lot of rock samples and soil samples were brought back, and within those lunar samples, zircons were found, and these were dated with the uranium-lead system, just like zircons here on Earth, and these were found to be around 4.5 billion years old. So these are slightly older than the oldest zircons on Earth, which is pretty incredible. It really testifies to the fact that Earth is a really dynamic system, whereas the moon has been sort of sitting there for a while and hasn't been strongly impacted by plate tectonics and things like that. But what's cool about this is if you compare these numbers, the surface of the moon is nearly the same age as our solar system. It's nearly the same age as Earth. So how did the moon form, and what's its relationship to the Earth? There's been two big hypotheses that were suggested to explain this. They have different names. One of them is called the fission hypothesis. The idea here was that early Earth was spinning so fast that you have this chunk of Earth sort of beating off and becoming the moon, sort of separating off so that you have two structures, one rotating around the other one. This is a pretty simple suggestion, but when you actually do the math to see if this could work, it really requires this Earth and moon system to be spinning extremely fast, and it's unlikely that this actually played out. The other idea is called the capture hypothesis. What this idea is that you have the Earth sort of forming close to its current position, and then the moon as essentially this irregularly orbiting planetesimal that was caught up in Earth's orbit. So, but one of the things that's tricky about the capture hypothesis is that this is only a very narrow range of trajectories where this could be possible. Most situations the moon will collide right with Earth and join the Earth, or it will fly right past the Earth and then keep orbiting around the sun and go far away again. So we can think about these two hypotheses too and what their predictions for the differences between the chemical composition of Earth and the moon are. This fission hypothesis, right, is saying that the Earth comes from the moon, so the Earth and the moon should have exactly the same chemical composition. However, this capture hypothesis suggests that the moon formed from somewhere else in the solar system, probably somewhere that was further away and may have more volatiles or other signatures of a different formation further away from the sun. So this is a comparison of what we know about the composition of the moon versus the composition of the Earth. What we see here is that there's a lot of silicon and oxygen in lunar samples as well as in the moon. But the moon itself has a lot less iron overall than the composition of the Earth. We know that a lot of this iron is in Earth's core, so that's one potential explanation for why Earth has a bit more iron. However, they're not dissimilar overall. The moon has lots of magnesium, it has a good amount of calcium, but when you start looking at the more trace elements, that's when you start to notice there are some significant differences. So one great example of this is potassium. So potassium is one of these what are called moderately volatile type of elements. That means potassium right now is a major component of sea salt. It's found in rocks. So we associate it in our lives with being part of solids. However, you don't need to increase the temperature very much for potassium to become a volatile element and turn into a gas. So if we look at potassium here on Earth, it forms essentially 3% to 4% of the rocks on Earth's crust, whereas similar rocks from the moon, it's only 1% or so. So there's some big difference in the amount of potassium on Earth versus on the moon. the moon is also depleted in lots of other volatile elements. So the fact that it's missing this volatile potassium implies that it's missing a lot of other volatile elements that make up our atmosphere, like carbon and nitrogen and oxygen. So this chemical composition for lunar samples is a challenge because it's not consistent with either the fission hypothesis or the capture hypothesis. For one, there are some pretty major differences between Earth and the moon. So it's not like the moon just formed from Earth and retained the same composition. At the same time, this capture hypothesis is hard to explain because the moon is really depleted in the volatile elements like potassium. And if we think it formed from potentially further away in the solar system, it should have more volatile elements, not less. So where do we go from here? So that video was made by BBC Earth. I'll link to it on Lalima. But the animations like those are derived from scientific modeling experiments that try to figure out what would happen if the moon and the Earth did in fact collide. This is kind of a halfway point between the capture hypothesis, where you have this gentle, embrace of the moon into its current orbit, and the fission hypothesis, where the Earth and the moon were originally one and separated. So in these simulations, the colors here are corresponding to temperature. You have Earth with its brand new crust. The magma ocean period has just ended, and along comes the moon, and it melts everything all over again. The moon itself, gets vaporized and turned into little, smithereens, small chunks of stuff, all of which are really hot. And so any potassium that's there is going to be vaporized and turned into a gas. Anything that's in Earth's atmosphere at this time is also getting vaporized and heading out into space. But this material is still affected by gravity, and so it's starting to orbit the Earth. But enough of this material is far enough away that it retains its position and isn't pulled into Earth. And this becomes the seed of the modern moon. You can see that Earth throughout this period is continuously molten. So this is the lunar impact hypothesis. One of the reasons why it's favored is it can explain a lot of the geochemical observations between rocks on Earth versus rocks on the moon. So for instance, the Earth and the moon have similar elemental compositions, and this is facilitated by this exchange of material after the proto-moon basically was vaporized during collision. But it also explains why the moon is low in volatiles, as signaled by potassium. Right? It's so hot in that original phase that all the potassium vaporized and was lost to space. This also can explain why the moon has less iron than Earth, if Earth's iron core formed just before impact. So you might be asking, why are we learning about this in an oceanography class? One reason is I think it's just really cool, but it also has a profound effect on the original atmosphere of Earth. Anything that came out of the mantle during differentiation of Earth is going to be lost during this collision, and the Earth is back to square one in terms of building an atmosphere and building an ocean. So the next video we'll talk about where the water in the ocean actually came from, but this is a good starting point to basically saying not here. So when you're reviewing the material of this video, make sure you pay special attention to how we know the ages of the moon and the Earth, and also how we can use geochemical measurements as far as the composition of Earth versus the moon to reject certain hypotheses about how the moon could be formed and advance ones like the lunar impact hypothesis that can explain the evidence.